Hello students, welcome to EPG Pathshala. I am Dr. Dipendra Sharma from MIT University, Gurgaon. Today we are going to talk on a module Hypothesis Testing, Type 1 and Type 2 Errors, One-tailed and Two-tailed Tests under the paper Quantitative Techniques for Management Decisions. After reading this module, students, you should be able to distinguish between Type 1 and Type 2 errors. You should be able to understand the concept of level of significance and power of test. You should also be able to distinguish between one-tailed and two-tailed tests. You should know about the suitability of the test statistics when sigma is known, when the sigma is not known, and apply a suitable test statistics when the data is qualitative in nature. Now, once the data is cleaned and ready for analysis, hypothesis testing is undertaken. It is used to resolve conflicts between two opposite views on a population parameter of interest. Hypothesis is an unconfirmed statement which needs to be tested empirically in order to explain any phenomena. It is based on assumption or on preconceived notion drawn from the existing theories or practices prevalent in the market. Type 1 and Type 2 errors. Since the decision of a hypothesis is based on the limited sample information, we are bound to make errors. Ideally, we would like to be able to reject the null hypothesis when the null hypothesis is false and do not reject the null hypothesis when the null hypothesis is true. However, we may end up rejecting or not rejecting the null hypothesis erroneously or falsely. That is, many a times the null hypothesis is rejected when it should not, or choose not to reject the null hypothesis when it should be. Principally, while deducing inferences about the population, there is always a threat associated that a wrong conclusion is being made as the decisions are based on a limited sample information. This may cause two types of errors, namely type 1 error, which is denoted as alpha, and type 2 error, which is denoted as beta. The following table summarizes the various decision circumstances surrounding the type 1 and type 2 error. Students, if you see in this 2 by 2 matrix, now there are 4 types of results that are possible. Let us discuss the first quadrant, which says that the null hypothesis is true and you are accepting a null hypothesis. It means that you have made a correct decision. The second quadrant, if we go right to the first one, is that the null hypothesis was true but we have rejected. It means that it has resulted into a type 1 error. The third quadrant reads as when the null hypothesis is false, when it should not have been accepted, we are accepting it. It means that we are committing a type 2 error. But when the null hypothesis was false and you are rejecting it, it means that you are taking a correct decision. Thus, we see that type 1 error occurs when the hypothesis is true, but our test rejects it. That the probability of having a type 1 error is called the level of significance. Type 2 error include when the null hypothesis is false, but the test does not reject it. Then the complement of the probability of occurring of a type 2 error, that is 1 minus beta, is called the power of statistical test. Thus, the power of a test is the probability of rejecting the null hypothesis when it is false and should be rejected, and it is represented as 1 minus beta. It is important to note that although beta is unknown, it is related to alpha, and an extremely low value of alpha will result in intolerable high beta values. What does mean that if we are trying to reduce only one type of error, it may lead to the increase in another type of error. So, it is advisable to balance the two types of errors. As a normal trend, alpha is often set as 0.05 level and sometimes it is set at a level of 0.01. Other values of alpha are rare. The level of alpha along with the sample size will determine the level of beta for a particular research design. However, the risk of both beta and alpha can be restricted by taking a larger sample. For a given level of alpha, by increasing the sample size, we will be able to decrease beta. Therefore, increasing the power of test, that is again 1 minus beta. In other words, as the sample size increases, both alpha and beta tend to decrease. However, for a given sample size, any attempt to reduce the likelihood of one error will increase the likelihood of other error. For a given n, alpha can be reduced only at the expense of higher beta. Similarly, the only way to reduce beta is to accept a high value of alpha. The optimal choice of alpha and beta depends on the cost of these two types of error, and determining these two costs is not always that easy. Typically, the decision regarding the optimal use of type 1 and type 2 error is made by the organization's management, where the job of the statistician is to conduct the hypothesis test for a chosen value of alpha. Let us see whatever we have discussed in theory with the help of some examples. Students, if the hypothesis read as null hypothesis, a person is free of malaria, so the alternative hypothesis is a person has malaria. In this case, type 1 error will occur when the medical test indicates that the person has malaria, that is, null hypothesis is rejected, but in reality, the patient is free from malaria, that is, H0 is true. In the similar case, type 2 error will occur when the test indicates that the person is free from malaria, that is, the null hypothesis is not rejected, where in reality he is suffering from malaria. Let us see what a one-tailed and two-tailed tests are. A hypothesis test will either be one-tailed or two-tailed. One-tailed test involves the hypothesis that can only be rejected on one side of the hypothesized value, that is, H0 where mu is either less than or equal to 0 versus an alternative hypothesis where mu is greater than mu naught. In this type of situation, null hypothesis may be rejected only when there is substantial evidence that the population mean is greater than mu naught. It is also known as right-tailed test since the rejection of the null hypothesis occurs on the right side of the hypothesized mean. Similarly, if the hypothesis read as that is null hypothesis where mu is greater than mu naught versus the alternative hypothesis mu is less than mu naught, it can only be rejected on the left side of the hypothesized value. Such tests are also known as a left-tailed test. In a two-tailed test, students, the null hypothesis can be rejected on either side of the hypothesized value of the population parameter, and it is written as the null hypothesis where mu is equal to mu naught versus alternative hypothesis where mu naught is not equal to mu naught, where mu naught represents the hypothesized value of the population mean. If the null hypothesis is rejected, it means that the true parameter does not mean the hypothesized parameter. So let us now see the hypothesis tests which are concerning to one population only. So hypothesis test of the population mean when the population standard deviation is known. This is situation 1, that we are going to conduct a hypothesis test in a situation when the population standard deviation is known to us. But student, as you know that it is not very common to be aware of the value of the population standard deviation. However, there are instances when is considered fairly stable and can be determined from previous experiences. Under such conditions, standard deviation is treated as known. A hypothesis test regarding the population mean mu is based on the sampling distribution of the sample mean represented by x bar. In particular, It uses the fact that the expected x bar value is equal to mu and the standard deviation of x bar is equal to sigma upon under root n. Also, in order to implement the test, it is essential that the sampling distribution of x bar follow the normal distribution. It should be remembered that x bar is normally distributed when the underlying population is normally distributed. If the underlying population is not normally distributed, students, then by the central limit theorem, x bar is approximately normally distributed if the sample size is sufficiently large or when the sample size is greater than or equal to 30. The hypothesis testing procedure simply enables us to determine whether sample evidence is consistent with the hypothesized under the null hypothesis. Consider the hypothesis H naught mu is equal to mu naught versus alternative hypothesis where mu is not equal to mu naught, where mu naught is the hypothesized value of the population mean. If the given value of the sample mean, that is x bar, from mu naught, it does not necessarily mean that the sample evidence is inconsistent with the null hypothesis. Perhaps the difference can be explained by pure chance. The basic principle of hypothesis testing is to first assume that the H naught is true and then determine if the sample evidence contradicts this assumption. This principle is analogous to the scenario in the court of law where the null hypothesis is defined as individual is innocent and the decision rule is best described innocent until proven guilty. The value of test statistic for the hypothesis test of a population mean mu, where the population standard deviation sigma is known, is computed as that z is equal to x bar minus mu naught divided by sigma upon under root n, where mu naught is the hypothesized population mean. Hypothesis test of a population mean when population standard deviation is known. So under this topic what we are trying to say now, we need to conduct a hypothesis test of the population mean when the population standard deviation is not known to us. Because so far we have considered hypothesis test of those population mean under the assumption that the population standard deviation was known to us. But in most of the business cases, population standard deviation is not known and we have to replace it with the sample standard deviation represented by small s to estimate the standard error of x bar. When sigma is unknown, the test statistics for testing the population mean is assumed to follow that is a t-test with a certain degree of freedom distribution. When the sigma is unknown, the test statistics for the population mean is supposed to follow a t-test, where when we are following a t-test, a new concept, that is a concept of degree of freedom, also comes into existence. And its value is computed as t at a given level of degree of freedom is sample mean minus mu divided by the standard sample deviation divided by under root n. As I just told you, where small s represents the sample standard deviation, df, which is representing your degree of freedom, and mu is your population mean. Another situation that arises during the hypothesis testing is when the population proportion is given to us. Sometimes the variable of interest is qualitative rather than quantitative, while the population mean mu describes the quantitative data. Population proportion represented by P is used as a descriptive measure when the variable under the consideration is qualitative in nature. It is defined as the probability of success, that is, probability of a particular outcome. As in the case of population mean, we estimate the population proportion on the basis of its sample counterpart. Population proportion is estimated on the basis of its sample proportion represented by P bar, where P bar is x upon n, where n is the number of success in n trials. Here, it is important to note that although P is based on binomial distribution, but it can be approximated by normal distribution also in case the sample is large. The condition should be honored for it is that the multiplication of n into p should be greater than 5 and n into 1 minus p should also be greater than 5 or equal to 5. In case the sample size is not large enough, then the method suggested here for statistical inferences about population proportion students may not be valid. Since the value of p is known, sample size requirement is tested under the hypothesized value of population proportion p0. In case the sample size is large and the normal distribution approximation is justified, however, when the sample size is not deemed large enough, the statistical method suggested here for the inferences regarding the population proportion are no longer valid. We know that the mean and the standard deviation of the sample proportion p bar are given by E, expected value of p bar is equal to small p, and standard deviation of p bar is under root of p upon 1 minus p and n as the formula suggests respectively. If p is equal to p0, then the normal approximation of the distribution of p bar is justified. The sample statistic for p is defined as follows. The test statistics for the population proportion p is assumed to follow the z distribution. Thus, the value is calculated z is equal to p bar minus p0 upon under root of p0 multiplied by 1 minus p0 divided by n, where p bar is equal to x upon n. P0 is the hypothesized value of the population proportion. Now coming to the examples or trying to understand the theory with the help of some examples. So let us discuss example number 1. Consider the following hypothesis which read as that a person is free of disease. Alternative hypothesis read that a person has disease. Suppose a person now takes a test medically that attempts to detect the disease. Discuss the consequences of a type 1 and type 2 error. In case of type 1 error occurs when the test indicates the person is having a disease, that is, a null hypothesis is rejected, whereas in reality a person is free from disease. This is also referred as false positive. In case the type 2 error occurs, that is, when the medical test shows that he is not having any disease, but in reality he is having the disease. It is also known as false negative. Let us take another example in where the null hypothesis reads an accused person is innocent. Consequently, the alternative hypothesis will be an accused person is guilty. So in case type 1 error is a verdict that finds that the accused is guilty, rejecting the null hypothesis when he is actually innocent. The type 2 error is due to the verdict that concludes the accused is innocent when in reality he is guilty. In the third example, we see that there is a research analyst which disputes a trade group's prediction that back year spending will average Rs 606, that is 606.40 per family this year. She believes that the average back to school spending will significantly differ from this amount. She decides to conduct a test on the basis of random sample of any 30 households with school-age children. Now, analyst concludes a mean as Rs 622.85. She also believes that the back-to-school spending is normally distributed where sigma is of Rs 65. Here we have to specify the competing hypothesis in order to test the research analyst claim, and also we need to calculate the test statistics. So it is desirable here to determine if the average is different from the predicted value of 606 rupees 40 paisa. Therefore, we specify our null hypothesis as, consequently, the alternative hypothesis read as mu is not equal to 606.40. For the second part, note that x bar is normally distributed since it is computed from the random sample drawn from a normal population. Since sigma is known, The test statistics follow the standard normal distribution and its value is calculated by the formula that we have just discussed. We know the values of x bar, mu naught, sigma and n. By putting those values in the respective test statistics, we can find a value of z which comes out to be 1.39. In another example, the director of a management institute wonders if his students study less than the 1981 national average of 24 hours per week. He randomly selects 35 students and asks their average study time per week. He calculates a sample mean of 16.37 hours and a sample standard deviation of 7.22 hours. We need to specify the competing hypothesis to test the director's concern, and we also need to calculate the appropriate test statistic. So, this is the case of one-tailed test where we could like to determine if the mean hours studied is less than 24 hours, or we can write it where mu is less than 24. Therefore, the competing hypothesis will be as mu naught mu is greater than or equal to 0 and alternative hypothesis mu is less than 24. The test statistic that we are going to use here is that it is normally distributed as the sample size is greater than 30 specifically and n is 35. The test statistic will be that t degree of freedom we are going to take here 35 minus 1, that sample mean minus mu divided by the standard deviation upon under root n. You get a value of t as minus 6.25. A population magazine asserts that fewer than 40% of the households in India have changed their lifestyle because of escalating gas prices. A recent survey of 180 households find that 67 households have made lifestyle changes due to the escalating gas prices. Develop the null hypothesis and calculate the value of test statistics. So the null hypothesis will be by the given data. Here we are going to use not mu, where we are going to use a proportion that is less than 40%. P will be less than 0.4. So the null hypothesis become P is greater than or equal to 0.4 and the alternative hypothesis become P is less than or equal to 0.4. The test statistic we are going to calculate by using the formula related to proportion. So by putting the values, respective values in the given formula, we get a value of 0.76. How have we calculated P bar? P bar is calculated by dividing 67 households by the total number of households that we are having. So you get a value of P bar that is 67 upon 180, which is equal to 0.3722. You should also see that we have also calculated the value or the assumption that the value of np0 and the value of n into 1 minus p0 should be greater than or equal to 5. So if you check these values, you will get that both the values are greater than 5. It means that we can go for this test statistics. Okay, so let us summarize what we have learned in this module, students. This module has made an attempt to provide you an understanding about the one-tailed and two-tailed tests. One-tailed test involves the hypothesis that can only be rejected on one side of the hypothesized value, whereas in a two-tailed test, the null hypothesis can be rejected on either side of the hypothesized value of the population parameter. It also exposes the students to the concept of type 1 and type 2 errors and the related concepts to them, that is about the level of significance and the power of test. Further, the insights are related to various test statistics related to different situations are also provided in this module. It provides test statistics for population mean when the population standard deviation is known and in the situation when it is not known. It also discusses the test statistics under the condition when the data is qualitative in nature. Thank you, students.